Hello everyone, myself Ms. Vinita Janardhan Rao, Assistant Professor in Mathematics from Ganpat Pasikar College of Education. I welcome you to third module of Elementary Combinatorics, which is Strong and Weak Induction Part 1. In this module, we will be discussing about weak induction principle and few examples based on it. Let us see what are the steps which are involved in weak induction principle. We have two steps over here, that is the initial step and the induction step. In the initial step, we prove that the statement is true for the smallest value of m for which it is defined, usually 0 or 1. The induction step is wherein we prove that from the fact that the statement is true for n, it follows that the statement is true for n plus 1 as well. First example, for all positive integers n, 1 square plus 2 square up to m square is equal to m into m plus 1 into 2m plus 1 divided by 6. So the first step that we have over here is the result for m equal to 1. Now when we take m equal to 1, here on the left hand side we get only 1 square, that is the first term. So left hand side is equal to 1. Let us check what is the right hand side. The right hand side will be, when we put m equal to 1, we will get 1 into 1 plus 1 which is 2 into 2m plus 1 which is 3 divided by 2 which is nothing but 1. So in this case we see left hand side is equal to right hand side, therefore result is true for m equal to 1. So this is the initial step. Now we prove the induction step, wherein first we have to assume that the result is true for some n. Assume the result true for some m, that is 1 square plus 2 square up to m square is nothing but m into m plus 1 into 2m plus 1 divided by 6. Next we are going to now prove with this assumption that this result is true for set of m plus 1 integers. So to prove that 1 square plus 2 square up to m plus 1 square is equal to, now instead of m we have m plus 1, so this will be m plus 1 into m plus 2, then it will be 2 into m plus 1, so that is 2m plus 3 divided by 6. Let us consider the left hand side, which is 1 square plus 2 square up to m plus 1 the whole square. Now the term previous to this m plus 1 the whole square is nothing but m square. So it is 1 square plus 2 square up to m square plus m plus 1 the whole square, which is equal to, if we see this sum up to m, we have assumed that the result is true for set of m integers, that is this sum is now m into m plus 1 into 2m plus 1 divided by 6, and we have m plus 1 the whole square. Now we just have to solve this equation in order to get your right hand side. Okay. First of all, you will see that in both the terms m plus 1 is common. So let us write it outside. We have m into 2m plus 1 divided by 6 plus m plus 1. We'll solve this further. So this is equal to m plus 1 into, okay. Now we'll multiply that 6 to m plus 1, we will get m into 2m plus 1 plus 6 into m plus 1, which is 6m plus 6 divided by 6. Now when we solve this further, we will get a quadratic expression whose factors we can compute, and this value is nothing but it will be 2m square plus 7m, 2m square plus 7m plus 6. This is what we get when we multiply these terms and combine them together, of which we have to find now the factors. So we will get m plus 1 into 2m plus 3 into m plus 2, the whole divided by 6. And that is what we wanted to prove. If we see over here, we had to prove it is m plus 1 into m plus 2 into 2m plus 3 divided by 6, which is nothing but your right hand side. So we see that the result is true for m plus 1 integers. So therefore, by weak induction principle, the result is true for all positive integers. Second example, for all positive integers n, the number of all subsets of this box n is 2 raised to n. Now with this notation, box n refers to the set starting from 1, 2, 3 up to n. We have to show that all the subsets of this set n is 2 raised to n. Now again, in order to prove this, we will follow method of weak induction. The first step is we have to prove the result for n equal to 1. For n equal to 1. So when we consider n equal to 1, it is nothing but this set, box 1, which is singleton 1. Now if we count the number of subsets of the singleton 1, it is nothing but the trivial subsets, that is empty set and the whole set. So the count of all the subsets is nothing but 2. Okay. So the number of subsets of 1 is equal to 2. 2 is nothing but 2 raised to 1, right? So we see that the number of all subsets of box n is in this form, 2 raised to that particular value, which is 2 raised to 1. So therefore, the result is true for n equal to 1. Now we assume that the result is true for some value n. So assume the result true for n, that is number of all the subsets of this set n is 2 raised to n, and now we have to prove that the result is true for n plus 1. To prove that the result is true for n plus 1, that is number of all the subsets of box n plus 1 will be 2 raised to n plus 1, like that. Now in this case, what we'll do is we will divide your subsets of box n plus 1 into 2 classes. Class 1, wherein it has all the subsets which do not contain n plus 1, and class 2, wherein we have all the subsets that have element n plus 1. So divide the subsets of n plus 1 in two classes, class 1 all the subsets that do not contain element n plus 1. Okay, and class 2 all the subsets that have element n plus 1. Now in class 1 whatever subsets that we have which do not contain n plus 1, that means they are the subsets of n, right? And by our assumption the number of all the subsets of n is nothing but 2 raised to n. So those that do not contain n plus 1 are also subsets of n, and by our assumption it is 2 raised to n. Okay, and those contain n plus 1. So those that contain n plus 1 consist of n plus 1 and a subset of n. However, that subset of n, see this subsets of n, it can be any of those 2 raised to n subsets of n. Okay, so however that subset of n can be any of the subsets any of the subsets 2 raised to n of n. So what happens to the number of the subsets of box n plus 1? It is once more 2 raised to n. So altogether the subsets that we have of this box n plus 1, it is nothing but from class 1 we get 2 raised to n subsets, plus from class 2 again we have 2 raised to n. So which is nothing but 2 times 2 raised to n, which is 2 raised to n plus 1 subsets. So in this case we prove that the number of all the possible subsets of box n plus 1, it is of that form 2 raised to n plus 1. So therefore the result is true for n plus 1, and hence by weak induction principle, by weak mathematical induction, the result is true for all positive integers. Now although these steps look simple, that is we have initial step which is important step and then we come to the induction step. Okay, but there are certain cases wherein if we apply this weak induction principle without proper knowledge, we might get some errors. Like in the example, okay, for suppose we are trying to prove that 2n plus 1 is divisible by 2. Okay, actually we know that 2n plus 1 is not divisible by 2. But if we proceed by big induction principle by skipping the initial step, okay, what does the initial step gives us? That if you put n equal to 1, clearly we will see that 2 into 1 plus 1, which is equal to 3, it is not divisible by 2. But if we skip that initial step and directly jump to the induction step, wherein we are assuming that 2n plus 1 is divisible by 2 for some n, and we are trying to prove that 2 into n plus 1 is also divisible by 2. So if we try to do that, here we will get 2n plus 2, 2n plus 2, which is divisible by 2. Okay. So this is the reference book that I followed, Nicholas Bona, A Walk Through Combinatorics. Thank you.